Hello, it's Keith here. Today we're going to be looking at the Game Boy and the Game Boy Color, and we're going to do a minimal example to create Hello World onto the screen. Now, unfortunately, unlike systems like the MSX and the Amstrad, we've got no firmware to do work for us, so we're going to have to set the screen up, define our font, really do everything ourselves. So the code's going to be a little bit larger than usual, but that's what we're going to be dealing with. So first, let's see our code actually running today. Now, because the Game Boy and the Game Boy Color are virtually the same system, we can write a version that will work on both. So let's see it running now. So here's the Game Boy version. You can see we've got Hello World here. We've got some corruption here. This was the Nintendo logo. We've actually remapped the tiles, so that's why we've got some weird text there. So that's the Game Boy version. And here's the Game Boy Color version. And you can see it's working fine on both. Now, the way it works is we've got a symbol defined. Build GBC will define the Game Boy Color version. This changes the palettes and some other little things like that. But if that's not defined, we're just defining the Game Boy version. Now, I use batch files to do my compilation, and I define one of the symbols within that batch file. We'll have a look at those later on, though. So that's how we can run our Hello World example. Now, you can see the code is quite long. We're going to go through it in sections and discuss what each part does, and so hopefully through that we'll be able to see how we actually get things working. Of course, as always, you can download all the source code for today's example from my website, and also this development environment that I've set up. I use Notepad++ and some batch files to actually compile and run on the emulators, as you saw. So all of that's available to you. Anyway, let's start looking at the code. Now, at the very top here, we've got some simple definitions. Now, when we want to draw characters to the screen, we want to be able to print a string. So we need to remember where the last character was drawn, so we know where the next character is going to be drawn. So we're going to have to do that ourselves. So what we're doing is we're defining 2 bytes of memory at C000 and C001 as X and Y for our position to draw the next character. The C memory range here is, of course, RAM within the Game Boy. Now, when it comes to the start of our cartridge, the first byte in our outputted ROM file, outputted binary, is actually the first byte of the cartridge memory. Now, the first few bytes are the RSTs. The Game Boy doesn't really need them. It can use them, but it doesn't need them. And the interrupt handler RST7 doesn't operate on the Game Boy. It's actually got its own special interrupt, which we can see just below. So I'm defining an origin here for 0, but then I'm skipping to origin 0040 in hexadecimal. And so that will just fill the area here with 0 bytes, at least with VASM. If you've got a different assembler, you might need to do a DS or something like that to pad that out. But with VASM, this works in this way. Now, we've got various interrupts here. We're not going to be needing any interrupts for today's examples. All I'm doing is I'm putting a return from interrupt at each of these positions. So this is our actual interrupt handlers, which we're just effectively disabling here. Now, our true code starts at hexadecimal 100, 256 bytes in. Now, the first 4 bytes here are the start of the program cartridge. So this is the address that the Game Boy hardware will execute when the cartridge starts. So we've only got 4 bytes. So all we can do at this point within those 4 bytes is jump to our actual program code, which is down here at this label called begin. Now we've got an important bit. This is the header of the cartridge. So we need to put some bytes here. And if we're going to run with BGB, the emulator here that I'm using, this is a fairly accurate emulator, and it does check the things that the true Game Boy does check. If we're using Visual Boy Advance, we can be a bit more flexible here. Now the Game Boy checks a few things. The first one is it checks the logo of Nintendo. Now the cartridge shows the Nintendo logo when it starts up. That's why sometimes if your cartridge isn't in correctly, you'll get some kind of weird glitchy block or corruption. Now once that shows, if it's not valid, it's checked against the internal copy of the Nintendo logo within the Game Boy. If it doesn't match, then the cartridge doesn't boot. And I think the reason for this is I suspect it's a trick. If you replicate the Nintendo logo, then you're breaching the copyright on the Nintendo logo. And so by checking that that's valid in the cartridge, they're effectively using the copyright law, I think, of the Nintendo logo protection to protect the cartridge itself, because if you don't have that logo, it won't boot. So anyway, we've got to have that valid logo if we're going to boot on a real Game Boy or on the BGB emulator, but we don't necessarily need to on the other systems. The other thing we need is a valid checksum. This header checksum is the important one. The global checksum I don't believe is used, but the header checksum is. Again, Visual Boy Advance won't check it, so we're just setting it to 0 here, but BGB does, and we're going to use a little program that fixes this for us and just generally makes everything work okay. Now, we need to specify a few other things as well. If we're using a Game Boy Color, we need to specify hexadecimal 80 here. If we're just a regular Game Boy, a 00 is fine. We've got manufacturer codes, Super Game Boy flags, a cartridge type here. We're specifying cartridge type 2 here. You can see there's a whole wide variety of options here, though, if you want more advanced types. Now, cartridge 2 is fairly advanced. We've got a memory mapper here and some extra RAM, so this is good enough for our tutorials and probably more than you're going to need. We're specifying a cartridge size here. We're actually specifying a 128K cartridge, which is pretty big, so you're not really likely to need more than that for your beginners games at least. And also we're specifying some RAM here again. 32K of internal RAM is a very advanced cartridge really. So you can change some of these if you need to, just depending on what you're requiring. But if you're just looking to get started with a Hello World or a simple game, I think this will be fine for you. So once we've got past the header, we've got the start of our code here. Now the first thing we're doing is we've got a no operation here, just adding, this is just padding to make things more reliable. Then we're turning off interrupts. Now what we're doing is we're loading a stack pointer. Now, as I said before, C000 onwards is memory. There's some special memory at the very top of the data range, and we're using that for our stack pointer. So this will give us a valid stack so we can do calls and things essentially. What we're doing next is we're starting to initialize the tile map and also the cursor position for our text drawing. So we're loading the accumulator with 0 by XORing the accumulator, and then what we're doing is we're setting FF42 and FF43 to 0. This is the position of the tile map. As the tile map scrolls, you would sort of see half a tile and things, but we don't want anything like that. We just want it at the 0 position, and that's what we're doing here. Because the accumulator is already 0, we're then setting X and Y of the cursor position to 0. Okay, what we want to do next is we want to start defining our font, but before we can do that, we need to check if the system is in VBlank. And what we're doing here to do that is we're checking memory address FF44, and this will return the current scan line. If the scan line is at 145, then we're in VBlank. If not, we're going to keep waiting. Once we are in VBlank, we're going to turn off the screen. What we do to do that is we address memory FF40 and we set bit 7 to 0. So that's what we're doing here. And that turns the screen completely off, because then we don't need to worry about VBlank. We need to be in VBlank for certain kinds of memory writing. So by turning the screen off at this point, we now don't need to worry about that. What we're going to do is we're going to define our font. Now our font's down here, we're reading it in from a file. Now this is a 1-bit per pixel black and white font, so it's very straightforward. There's 8 bytes for the 8 lines of our 8x8 pixel font. Effectively it's a Spectrum font. It's the same font I use in all of the tutorials, and it's got 96 characters. So the first character within this font file is the space character, so characters 0 to 31 are unused. The first character is 32 space, and it goes all the way up to 128. So it's pretty much a full ASCII font for characters 32 to 128, just missing the first 31. So we're defining the source of the font within this assembly file. We're defining the destination at hexadecimal 8000 in VRAM. Now this is the start of the pattern definitions that are used to define tiles. Then we're defining the length in BC. And what we're going to do is we're going to read in each byte from the bitmap font, and we're going to store it to HL. Now we're using a special Game Boy command here called load and increment. So what this does is it writes the byte from A into HL and then increments HL, and that's why I'm using HL as the destination and DE as the source in this case. Now you'll notice we're writing the bytes twice. We're reading once, but we're writing them twice. Now the reason for this is, while the font is a 1-bit per pixel font, the Game Boy uses 2 bits per pixel. It uses them in bit planes, and what this means is each line contains 8 pixels worth of data, and the first line we write is the first bit per pixel, and the second line is the second bit per pixel. So you might not understand that at this point, but you maybe if you try changing the A to different values here, you'll see what actually happens. For example, if we load A with 4 ones and then 4 zeros here and run this again, you can now see the left hand side of each of our tiles has changed to red. And what we've effectively done is we've set the second bit of the first 4 pixels to 1 that makes up the colours. And so we've actually now selected either the second colour or the third colour, depending on whether the first bit plane was set or not. So say it's a little bit tricky, bit planes, but I've got other documentation on bitmap graphics on the Game Boy, so please take a look at that if you want to see more. Anyway, once we get to this point, all you need to know is our font is now defined as the first 96 tiles within the Game Boy. Okay, now we need to set our palette, and this is the first time the fact that we are running on a Game Boy or a Game Boy Color becomes important, because of course the Game Boy Color has colour. Surprise there. So if we're using the Game Boy Color, we're going to use a function called set Game Boy Color palettes, which we'll have a look at in a moment. We're going to run it twice. We're going to run it first for palette 0, which is used by the background basically, and then once for palette 7, which is used by our font, and you'll see why in our font code later on. Now we're running this function and we're basically using the same palette definition for both palette 0 and palette 7. Now each palette contains 4 colours and each colour contains 2 bytes. So that's 8 bytes per palette, and that's why we're setting C to either 0 or 7, and we're multiplying that by 8 to select the memory address of the palette that we want to change. Now on the black and white Game Boy we don't do that. The black and white Game Boy's colours are defined by FF47, FF48 and FF49. FF47 is the background, 48 and 49 are the sprite data. Now we're not actually using sprites here, but just for completeness I'm defining them. So we're using LDI again, so we load HL with FF47. We set the background to this definition here, and the way this works is these 2 bits define colour 0, these 2 define colour 1, colour 2 and colour 3. Now 1 sets the pixels to the darkest value, and 0 sets them to the lightest. So we're defining the background as black and the foreground as white here. And you can see that just here. If I set this to 10 instead of 00, our font has now gone a dark grey. Now what we've done here is we've loaded HL with FF47, and we're using this increment command again. So we're setting the background and object 0 to this same colour, then we're flipping the bits and we're setting object 1, which is the alternate sprite palette, to the opposite. So if we want to invert flash a sprite, maybe if our character's been injured or something, we could do that relatively easily. But as I say, we've got no sprites in today's example. Now we've defined our palette and our font, we can turn the screen on. So that's what we're doing here. We're just setting bit 7 of FF40, which we reset here. We don't need to worry about VBlank because of course the screen's off. So that will turn the screen back on. And now we're going to print our message to the screen. We'll have a look at that in a moment though. Now about those palettes. So here's our Game Boy Color palette. You can see it just here. Now the palette definitions use 2 bytes, 5 bits per color. So you've got blue here, you've got green and got red, and the top bit is unused. Now you'll see this last definition here is all ones. This is my end of palette command, if you will. So what we're doing here, we started this with the C already pointing to the palette we wanted to change. And then we're loading in HL to GBPAL because we're using the same palette definition both times in this example. We then load in 2 bytes from HL, we're using LDI again, incrementing HL once we've read in. Now we can't load directly to E with LDI, so we're doing 2 commands here. So we load in A, load to E, load in A, load to D. We then increment A. Effectively, this is a trick. We've already loaded D with A, so we don't need A anymore. If we increment A, we're effectively comparing to 255. Now, the top bit will usually always be 0, but in our last definition, it will be 1. And so what we're effectively doing is checking if we've got this last byte read in here. And if we have, we just return. If we haven't, we've got a palette definition we want to send to the Game Boy Color hardware. The Game Boy Color hardware uses 2 addresses for its colors. FF68, which selects the color we want to change, or the byte within the color, sorry, and FF69, which is the new value. So remember I said each definition uses 2 bytes. So we're using that C again, which we defined before we called this function. We write that to FF68. We then increment HL. We then write the new byte value, the low byte value first to FF69. We then decrement HL, pointing HL back to FF68. Increment C, because we're going to write the second byte, and do the same again, this time writing the high byte from D. So we're doing this twice. Basically, we are setting the pair of bytes to the definition read in here for C as it was passed to us. We're incrementing C each time, so we're ready for the next definition. Now, you could define all of the palettes in one go. You just need a much bigger list here. Now, in this case, it wasn't efficient to do that because it would have taken more memory, and I only wanted to set palette 0 and palette 7. So that's what I've done here. Now, I could have used LDI here, but I decided not to because, again, we can only do LDI from the accumulator. And so with all these commands, I thought it would be better to just do inc and HL directly themselves. Anyway, so that's how we're loading in our palettes here. Now, we've got to the point now where our screen's working. What we're going to do is we're going to need to print a character to the screen. So the tile map within the Game Boy is pretty simple. Now, effectively, the tile map starts at hexadecimal 9800 in memory, and each line of the tile map is 32 tiles wide and 1 byte per tile. Now, although the screen is only 20 tiles wide, the tile map's actually bigger for scrolling and things and for convenience. So what we need to do to calculate the memory address for any given tile within the tile map is to take 9800 in hexadecimal, add the Y position times 32, because there's 32 tiles wide, and then add the X position. Now that's what we're doing in that code, but we're doing it with bit shifts because that's the efficient way of doing multiplication within the hardware. So what we're going to do is we're going to load the Y position into B here. We're going to load the X position into C here, but then we're also going to just check if the X position has already reached the end of the current line. And if it is, we're going to call this new line function just here. Okay, so now what we're going to do is we're going to take the Y position and we're going to repeatedly rotate it to the right until it gets to this position here. This is effectively multiplying the Y position by 32. Then what we're going to do is we're going to OR in the X position here, and then we are going to add the tile base, which was 9800, to BC, because BC now equals the Y position times 32 plus the X position. Now at this point, HL will point to the memory address within the tile map, within our system memory, for the tile that we want to change to our character. Okay. Now what we need to do is we need to subtract 32, because remember our font had no characters below 32, so 0 was our space character. And then we need to wait for the hardware to be able to write to the video memory, because again the video memory is locked at certain times. We're going to have a look at that in a moment. So then we just store our character number to HL memory address here, and that will show the character on the screen. That's all we need to do for the Game Boy, but for the Game Boy Color we need to set our palette. How do we do that? Well, on the Game Boy Color, the memory address FF4F defines the video banking, and so what we can do is we can turn on the extra video RAM just by writing a 1 to FF4F. We do that just here, and then this will switch in the alternate memory, and each of those memory addresses has a matching byte now within that extra bank that's at the same memory address. So we wrote the tile number to 9800 before, and now if we write a 7 to the same memory address, we're effectively setting palette 7 for that same tile. Now there is some other functionality within there, like you can flip the tiles and things. We're not going to look at that at this point, but that's what we're doing here. We're using the palette 7 by writing to that address again, and then we just write a 0 to that same address in BC, FF4F, and that turns off the VRAM bank so that the Game Boy is back to normal. And there we go, that's how we draw a character. Very straightforward. Now we're going to extend that to allow us to print a string, because once we can print a character, we can print a string pretty easily. So we're going to use HL to point to our string, you can see just here, and we're just going to load in from HL until we get to a character 255, and anything that's not a 255 we're just going to print to the screen, and that's how we get our hello world message shown on the screen. Now when it comes to compiling, we're just using VASM in these examples. We've got some little tricks here. We're disabling case sensitivity. We're checking to see if we've made a mistake where a command looks like a label. For example, if we've got our tab there, DI would be treated as a label, so we've got to check to make sure that doesn't happen. We are outputting to a binary file. We're calling it cart.gb or alternatively cart.gbc, and we're just creating a listing file which is for debugging. You don't need that. Now on the Game Boy Color for this example, you need to define a symbol called build GBC somehow, either on the command line like I've done here, or you can just include it in your code like that. Now we're specifying the Gameboy Z80, which we need to do for VASM, but once we've done all of that, we output to a binary file, and that binary file would be good to go if we're using Visual Boy Advance. Now if we're using BGB, that's the more advanced emulator which checks the checksums. We need to fix that checksum, and so I'm using a tool called RGB Fix, which I didn't write. This is a very good tool which does the job perfectly, and this will check a cartridge file and it will make sure it's got a valid checksum. That's what this /v does, and it's also padding the cartridge out with zeros, so it's doing the job of making a valid-ish cartridge for us. It's not going to check the code obviously, and I'm sure there's plenty of mistakes we could make that would still be invalid, but it's doing the job of getting the checksum and things correct for the cartridge, and that means BGB, the more advanced emulator, will happily run it for us, and that's what we're doing with this last line here. We're just starting BGB, running the cartridge. Game Boy Color version is basically identical. We've just got the definition for build GBC here. Now, as an added bonus, we're going to look at how to use the monitor tools. In my multi-platform series, we wrote a very simple monitor, and we can include that just like this here. And then if I just run this code, we'll see what those monitor tools do. Now, as well as our hello world here, you can see we've now got SPAF, BC, DE, HL, PC. And these are the primary registers within the Game Boy's GBZ80. So if we're creating a program and we're having some trouble and we don't know what's going on, maybe we need to see the state of the registers to try and debug it. So if we've not got a very good emulator, I think BGB does actually have a built-in debugger. I can't remember how to use it. But if we're using another emulator, or if we're using a lot of different systems, it's good to rely on our own tools because it gives us a consistent working method. And so we can use that monitor to just check our registers. And also if we want to check the state of part of our memory, just to check if things have loaded correctly or if things are getting corrupted, we can dump part of our memory. We've dumped address 0100 here, and we've got the bytes and then the characters here. And to do that, once we've included those tools, all we need to do is either call the monitor here, and you can see we can test that here. We've got A0, A equals 1 here, and you can see A equals 1 here. And then if we just change that again, we'll change it to 2. You can see it's changed to 2 here. So we're dumping the valid values of the registers to screen here. And then we've got this extra function here, which is memdumpDirect. It dumps the address in HL and it shows it to the screen. So if we change this to 200, maybe we could see if there is some data here at 200. That's probably our font data, possibly. Anyway, so that's how we can use the extra monitor tools to do things for debugging. Now, if you want to see more of those, please check out the multi-platform series where we looked at how they actually work. It's far beyond what I want to cover today. Anyway, that's how we can do a Hello World example on the Game Boy. A little bit long because of the initialization of the screen and the patterns, but you know, pretty simple example. So please go ahead and download this and get the development tools if you want. If you're interested in Game Boy development, I've got a whole series on the Game Boy, how to do basic things, and the GBZ80 processor, which isn't a true Z80, but it's pretty close. Anyway, thanks for watching today, and goodbye. If you enjoyed today's lesson, please check out my website. We've got tutorials, source code, and development tools for 6502, 68000, and Z80 systems, and a lot more systems coming in the future. We're going to be covering the 8086 and the ARM, and a few other things as well going forwards. And if you've liked this lesson, if you've got questions, comments, or suggestions on how it could be made better, please consider signing up to my forum. It's free, of course, and you can come along here and you can make suggestions, you can ask questions. And if you've got assembly projects you're working on, please let us know what they are. Maybe show off a few screenshots, tell us what things you've found interesting or what tricks you've come up with, because we'd love to know about it. Anyway, thanks for watching today, and goodbye.